Hi, my name is Joseph Van Tassel. I'm a research associate at the Texas Advanced Computing Center. Today, I'll be presenting on some work I did with my colleague, Professor Brady Cox at Utah State University, related to looking at the influence of different starting models on near-surface two-dimensional full waveform inversion. To begin, I'm going to provide some motivation to this topic by looking at a classic geotechnical problem where we have a site and we're interested in identifying the depth to rock to be able to assess our different design alternatives. So here we're looking at a slice into the ground and we're looking at depth along the vertical axis and distance here along the horizontal axis. And for this site, we can infer from local geology that we know there's a soil layer, a soil deposit over a rock layer down at depth. And the question that we're really trying to solve is, where is that soil rock interface? The way we may do this traditionally is to push a CPT or do a boring at our site to be able to identify that depth to that contrast. And if we do a CPT at our site, we then will extrapolate that measurement over some distance, some horizontal distance. However, where this really breaks down is if that interface is highly variable and that we see large spatial variability at our site. And we can really see that that CPT is only providing us a point measurement, and it's not really giving us any sense of how things are varying laterally. So the question becomes, can we do better than this? And one of the techniques that can be used to develop really an image of the subsurface where we're looking at the material properties for that whole two-dimensional slice is called full waveform inversion. And so here we have the same problem we were looking at previously. We have soil over rock. And then this is a site where we'll perform 2D full waveform inversion. And there are really two stages to full waveform inversion. First is the acquisition phase, and then the inversion phase. And so the acquisition phase looks like something a little bit like this, where we'll place sensors at the ground surface, shown with these inverted blue triangles here. And then we'll hit on the ground with some sort of source to generate seismic waves and propagate them across our site. And that's what's shown here in red. And what this might look in reality is we'll have some linear array and we'll place these geophones at the ground surface, and then we'll hit on the ground with a sledgehammer and to propagate those stress waves through the subsurface. With the goal here of measuring the time domain propagation of those waves across our site. And that's what's represented here on the right. Once we've made this acquisition, once we've acquired these waveforms, then we enter the inversion stage, where now we try to go from these waveform measurements on the right back to the subsurface model we're interested in, really with the goal of being identify the stiffness of the soil and the stiffness of the rock and their interface location. And it's important to note that this inversion stage is quite complicated. It's quite a difficult problem to solve. And this presentation and really this study is looking at ways of improving the rigor of that inversion. So let's start with the synthetic experimental setup. What did we do in this study? The objective, of course, is to look at different starting models on 2D full waveform inversion. To really assess that, we started by first creating a complex but a plausible synthetic model representative of the soil over rock classic geotechnical problem. And then we performed full waveform inversion using different synthetic models to see what their effect was on the inverted model. And so here's the synthetic model that we selected. The soil material here in the lighter color, and then the rock-like material in the darker color. And we can see that the soil and rock, the material properties are variable spatially, and also the interface, of course. Our acquisition here is 24 receivers at a 2-meter spacing with 25 different source positions, which is a pretty classic acquisition setup. And for our synthetic source, we're using a 15 Hertz high pass filtered spike, and you can see the time and frequency domain representation of that spike in the lower right. So now we go on to the inversion details. So as I mentioned, we're looking at the effect of different starting models on the full waveform inversion. And the three that we're looking at are the constant, the linear, and the MASW. That's what's shown here on the right in terms of their shear wave velocity, VS. And the goal here, of course, is to invert for all three elastic properties, VS, VP, and mass density. And we do that using a gradient-based optimization with a quasi-Newton scheme, LBFGS in this case, and a line search to establish our step length. We use a multi-scale full waveform inversion with 3 different frequency ranges with the objective to reduce cycle skipping and help us converge to a good solution. And we do all of this using the open source full waveform inversion software developed by Cone. So if we start with the constant starting model, we have before full waveform inversion up here at the top, and you can see the model itself, again, is a constant shear wave velocity throughout the entire domain. And on the right, we compare the waveforms from the synthetic model, the metal model we're trying to recover, that's shown here in black, that's the true answer. And then the red dashed lines are the waveforms that we get by propagating that stress wave through this before full waveform inversion constant starting model. And you can see, of course, that the red dashed lines do not agree with the black solid lines, which is indicating that there's a difference here between our starting model and the true model. And of course, reducing those differences is the whole point of full waveform inversion, where we will modify this before full waveform inversion model systematically to get a good agreement between the waveforms. Unfortunately, for the constant starting model, the full waveform inversion failed and no results are available. And this is really attributed to the distance between the starting model and the true model. They're essentially too different to be able to converge using this gradient-based optimization. The second model we're going to look at is the linear starting model. So that's what's shown here in the upper left. You can see the relative disagreement between the true waveforms and those generated from the linear model. However, the full waveform inversion was successful here. We're able to recover an after full waveform inversion model. And we can see on the lower right that the waveforms between the true model and the after full waveform inversion model agree extremely well. However, we see that there's no indication of a sharp contrast between our soil-like material and our rock-like material, which is, of course, important for the geotechnical decisions that we may need to make. So some limitations here. The final starting model we considered was an MASW-based, so multi-channel analysis of surface waves, to use that to develop a one-dimensional model, which we then extrapolate over the whole model's distance here. And we can see that we get very good agreement even before full waveform inversion in terms of their waveforms. And then, of course, after full waveform inversion, we get a slightly better fit. However, the model itself does not change significantly. And the important thing to note here is that we're really missing that concave down shape, or really any indication of a variable interface between the soil and the rock. And so to kind of show the linear starting model after full waveform inversion and the MASW starting model after full waveform inversion, and compare that back to the true model, we can see that while the waveforms for these models all agreed quite well, we can see that the models themselves do not exactly match one another. And so why is that? And that really comes down to the complexity of the full waveform inversion problem. We're dealing with a large number of unknowns, thousands in this case. It's highly nonlinear, highly non-convex loss function, which makes this gradient-based optimization very challenging. And then finally, we have an ill-posed problem, which means a unique solution is not guaranteed. And so let's look at an example of what these words really translate to. So here on the left is a convex loss function. This is the optimal case, so to speak, where regardless of where we start in this domain, here I'm just showing 2 different variables. Regardless of where we start, if we do gradient-based optimization, we'll converge to the minimum here at 0, 0. However, that's not the case we have with full waveform inversion. We know we have a non-convex loss function. And here's an example of a non-convex loss function. And the important point here is that wherever we start on this domain, we're going to converge for a different local minima, and we're not going to guarantee convergence to the global minima. This is very important. This is what we're essentially seeing with the effect of different starting models, is we're starting at different locations and converging to different local minima. So then the question becomes, well, how do we do better? How do we solve this problem more rigorously? One alternative that we've looked at is using machine learning, in particular a convolutional neural network, to develop a better starting model, a starting model that's closer to the true model, and therefore will hopefully converge to a better final model. And so we developed this convolutional neural network shown here on the left, and a large training set shown here on the right. And after we've done the training, this is what we end up finding. So if we take the true model's waveforms and give it to the neural network, the convolutional neural network, this is the prediction it applies. So we're seeing kind of the metrics we were interested in. We're seeing a sharp contrast between the soil and the rock. We're seeing the concave down shape, which we expect. We lose some of the fine scale details, but overall, we're getting a good approximation of the true model, and really a better approximation than we saw with either the linear or the MASW. And of course, more work needs to happen, but this initial work shows great promise. And so in conclusion, really 4 things to highlight. First is the starting model has a strong impact on gradient-based full waveform inversion. Second is that you will generally do better if you use a priori information. For example, the MASW model outperformed the constant model. And third, that the good waveform match does not necessarily guarantee that the true and inverted models are identical. And this is, of course, a consequence of the non-uniqueness. And then finally, future work is necessary for developing more reliable starting models and addressing non-uniqueness rigorously in full waveform inversion. And so with that, I'd like to acknowledge the financial support from the National Science Foundation, as well as the computational support from the Design Safe Cyber Infrastructure and the Texas Advanced Computing Center.